Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. Today we are going to continue and hopefully finish that part on tolerant retrieval. And if time permits, we might start also to look at how to build very, very large indices when the collection is huge. So I left you last time with wildcard queries, which is one of the features that an information retrieval system can have. And the idea is that you use the star as a joker symbol that replaces any sequence of characters. It's not exactly like a regular expression. So a regular expression would be the indicator of zero or more, like the clean star. But in that case, that's really more like a special character that replaces anything, right? So for example, if I say that's completely made up, of course, but if I say foo star ETH star bar, then this is all the sort of things that could be covered by that. So it's like you can imagine that like a gigantic end Boolean query with any possible, actually an infinite number of possibilities, right? But how do we do that? How do we expand our systems such that we support queries like this? So for example, if we start looking deeper at the sort of queries we can have, meaning where this joker symbol would be, it could be at the beginning, for example, economics, physics, that's an example. Or it could be at the end, like math, mathematician, mathematics, mathematical. Given what we have now, the standard inverted index that we built, and we have this B+3 structure that allows us to sort the terms, which one of the two do you think we can already implement now out of the box with the index we have? This one or this one? So who thinks, it's going to probably switch now to the next one. Okay, let's take this one. Who thinks that this one we can support with the current index, with the standard inverted index? If you raise hands, who thinks we cannot? I see raised hands, yes? You think we cannot? Anybody else? Sorry, that's exactly what I anticipated, the slide change. I mean this one. Who thinks we can support this one? And who thinks we cannot support this one? Okay, now I see raised hand. That's why the slide had moved. And now, who thinks we can support this one with the leading? Okay, who thinks we cannot? Okay, so the majority is indeed correct. This one is the easy one. This one, that's more complex, and I will show you later. So let's start with this one. Can anybody tell me how you would proceed with the current standard inverted index to solve that query? And then I will show you. Maybe on Zoom. Does anybody on Zoom know? So this one. Nobody on Zoom. Okay, let me just tell you. So imagine this is all made up. Of course, these are not real terms, but I kept it simple with a few characters. Imagine that this is the B+3 that we have. So the blue cells at the bottom, these are the actual terms in your standard inverted index. The ones in pink at the top are only for lookup, for the comparisons. And you can see that every time, actually, the pink values are just the leftmost from the right every time. So AC, BAD is the leftmost in the third one, CD, not quite actually, it's CD, I could have put CE instead. But it's correct because the comparison, I mean, the property of the B+3 holds that everything on the left is smaller and everything on the right is larger. Okay, so BA star is my query. So remember that all of these blue cells here at the bottom, they are ordered alphabetically, right? This is the property of the B+3, right? Everything is alphabetically sorted, and this gives us the limits between the three, and this is also alphabetically sorted. So if you look at this, BA star, in fact, what we are looking at is an interval, right? We are looking at the interval of all the words that come after BA and strictly before BB. Who agrees? Okay, so we're just looking at an interval. It turns out that with hash indices, we cannot support intervals, but with B+3s, we can. That's beautiful. So all we need to know, all we need to do is to look up at the two boundaries of the interval. So BA and BB. So this is somewhere here. So basically, it means that anything on the left of AC we can ignore. Right? That's certainly not going to contain anything of interest to us. Anything between AC and BAD that we are interested in, partially at least. And everything between BAD and CD we might also be interested in, partially. And everything after CD we are not interested. So you see now what we've done is that we just eliminated a few branches that we certainly will not need to look up. We don't even need to read them from disk. But the part in the middle marked as yellow, that we are interested in, right? So the two terminal nodes right here. So this we need to read from disk, but of course it's partial, right? It's going to be a part on the left that we are not interested in, and here we are interested, and here we are not, right? So I put in bold and green here, the ones we're interested in. So you see now, I just already did a selection here, and now for the leftmost and the rightmost, in this case, it's just 2. If it had been 4 of them, for example, we will only have to cut on the leftmost one and the rightmost one. And now we have the 3 that correspond to our wildcard query. And now we can look at the posting list and do the union or intersection. Who thinks intersection? Who thinks union? Yeah, union. And by the way, I said earlier a giant AND, but no, it's a giant OR, of course. It's a giant OR. Okay. So now, let's try the more difficult one. So now you probably see, because you correctly answered, the majority was correct, that we cannot easily do. There would be no other way than to just go manually through the entire alphabetical list and look at everything that ends with AC. But we cannot find any interval here because it would be all over the place, right? So that we cannot do. So the index is useless. It doesn't mean we cannot answer the query, but it would take forever to process it. So what can we do? Maybe we can build additional index structures that we don't have yet, but maybe we can build them in anticipation that people might have this kind of query. So what we do is that we reverse all the words starting at the end. We write all of the words backwards. Right, so like this, and resort it. Right, then we rebuild the entire tree like this. Okay, so we end up with something that looks like this. I didn't do any mistake. We mirror the words, resort them, and build a new B plus tree. That's another index. That's not the same one. It's another index. We have 2 indices now. We have the normal one, and we have the one that is mirrored, but with everything resorted. Now, can anybody give me the interval that I'm going to be looking for now in that B plus tree that has the mirrored terms? On Zoom, maybe? What am I going to look for? Yes? CA to C? Yeah, exactly. CA to CB, exactly. So you see, normally, yes, exactly. Somebody on Zoom agrees too. Yeah, that's the correct answer. So what we need to do, it's on strike again. Yes, exactly. So CA, I just reverse also that query. But you see that if I reverse it, that becomes CA star. And now we are back to a known problem that we know how to do. So I look at everything between CA included and CB excluded. That's exactly the same idea as before, meaning that everything that is on the left of BA, I can just ignore. I don't even need to look at the disk for that. If that in between, I can also ignore because that's before C. And between C and D, that I need to look at. And after D, I don't need to look at either, right? So everything will basically be in between. The only thing I need to load from disk is this here, right? That's very convenient. And now if I filter further, it's alphabetically sorted, so I can do that with a binary search here. And in logarithmic time of that small size. Now I have CA, CAB. These are my 2 posting lists. And now I can do the union. And again, I insist, this is another index. It's a second inverted index. It's no longer the standard inverted index. It's another kind of inverted index based on the mirrored terms. And I still have it point to the postings list, of course, as usual. And now I can read, right? So for AC and BAC. So basically in CA that corresponds to the term AC and CAB corresponds to the term BAC, right? Because I mirrored. And now we see that since I will return documents that contain the term AC and the term BAC, that does answer my query, right? Because I'm looking for everything that ends with AC. Who agrees that it solves the problem? Okay. So this is it. So now we know how to implement the leading wildcard queries, and we know how to implement the trailing wildcard queries. What about wildcards that would be in the middle of the word, like Zu star CH, right? So here we could consider a first approach of, again, trying to get back to a known problem. So we could try to find the words that start with the U and that end with CH, right? So I rewrite that as ZU star ends star CH. And then I do two lookups, one lookup with my normal B plus tree, the normal standard inverted index for all the words between ZU and ZV excluded, and all the words in the reversed tree between HC included and HD excluded, right? And then I do within each B plus tree the union and then the intersection between the results on the both sides. Who agrees? Okay. Do you think that in that case there will be any false positives? Who thinks there will not be any false positives in that very case? Okay. Who thinks there could be in general false positives? Some of you. Let me give you an example. This one, statistics, for example, with a star in here. Then we do statistar and star ticks. Can you give me an example of false positive that this is going to, like a false positive term that we're going to get documents for? I mean, basically something that would be returned by the rewritten query, statistar and starticks, but that would not match the original one. Yes, we have on Zoom. Statics. Yes, exactly. Statics would basically be returned by the rewritten query, although it does not match the original query. So now I introduced some potential mistake here that I might have false positives indeed, right? So it means that when that happens, it's okay. We might have false positives. We just need to add a post-processing phase to filter them out. So we just need to check that, again, in what we have filtered, now we need to execute statistics, so the original query. But this is going to be much easier because the size on which we post filter is much smaller than the entire collection. So it was still useful to have this index in the middle. But there is another way. That's, again, some smart people who figured things out. And this comes with yet another index, another one that's called the permuterm index. And the idea of that index is that instead of mirroring the terms, what you do instead is you rotate them. What do I mean with rotate? How do we rotate a term? Well, the idea is this. Imagine you write the letters of the term on a circle, and it comes back to the beginning, and you just put $1 in the middle. Then what we call a rotation would basically be $plants, that's the original one. And if you rotate on that circle, you rotate the place where you do the cut, then the T now is no longer at the end, it comes back to the beginning, then the ends, then the A and the L and so on. So these are all the possible rotations of my term, okay? And the idea is that if I want to execute that query, imagine that now I rebuild the B plus tree, but instead of being the standard B plus tree or of being my reverse B plus tree, I have a B plus tree that contains all the rotations of all the terms. Can anybody tell me which interval you're going to look up in such an index that would have all the rotations of every term in order to execute the wildcard query PL star T? What prefix do I need to look up in that permuterm index? Can anybody see it? Yes? Yes, the second one. More exactly, so the second one would be an actual match. So that would be a match. What would be the interval that you're looking for with potential other matches? Yes, exactly. I'm repeating for those on Zoom. We are looking for the interval between $T PL included and $T PM excluded, right? You basically start looking for the star. After the star, T dollar, and then you go back to the beginning, PL. So you will find $T PL AN, so that is contained in that interval. And then, of course, since you have the rotation, you know it's the rotation of plants, right? So you have the postings list that contain all the documents that contain plants. And you see that plant is an actual result in there. Who sees it? Right? This is how we solve it. This is called the permuterm index. So $PL star. So everything between $PL included and $PM excluded. There you go. And you can come back to plants. So of course, there could be several ways of implementing it. So in that permuterm index, either you point from every rotation to the original term, and then you look up the original term in the original index, or you directly put the posting lists in there, right? There's always a bit of a decision leeway in that sense, right? So you can point back, let's say we point back to the original term. Let's say I have another rotation for ETH, that would be $ETH, $ET, $TH$E, and $ETH$. And that's it. So now, basically, I do it for all of my 500,000 terms. Imagine I have 500,000 terms. So I compute all rotations of every one of these terms, and I merge them then into a single structure. And again, I'm of course going to use a B+3 in there so that I can efficiently look them up and including interval lookups, right? That's the sort of things that I could get basically. Now I have just two terms, ETH and plant. I have all the rotations of these two terms. And now anything I look for, it will basically find with this index the original terms that match what I'm looking for. Who is with me? Okay, this is called the permuterm index, right? Yet another index that we can have. In the end, the information retrieval system that we will have might have, I don't know, 5 or 10 indices, right? It's exactly the same thing with a relational database system. You can have plenty of different indices. It's really a decision on what indices do you actually build and what indices do you not build. These are decisions that must be made ahead of time, before you have visitors, before you have people who issue queries, right? Because building the index takes time, but if you took the time to build the index, then at runtime, this becomes available and you can do these lookups. Okay. Then let me show you yet another way. So the permuterm index, it's for the wildcard queries that would be in the middle of the word. Now imagine that I'm looking for all the words that have MPU in the middle. So of course, you could consider using the permuterm index. For example, you could look for MPU, everything that starts with MPU in the permuterm index. That might be a good strategy, right? But there is yet another way that's called K-grams. So the K-grams of a word look like this. So the 1 grams, that's easy, that's the letters. The one thing that you need to do is add $1 at the beginning and add $1 at the end. It's similar to what we did with the permuterm, right? The $1 is just a special marker that tells us this is the beginning, end, or the end, right? So here it's the beginning and another $1 for the end. So we have $COMPUTER $. Of course, after that you eliminate the duplicates, but this is the idea, right? Then the 2 grams, you have a sliding window with 2 letters. You have $C, then CO, then OM, then MP, then PU, then UT, then TE, then TR, and then R dollars. That is called a 2 gram or a bigram. Sorry, a bigram. Okay. Can anybody give me the 3 grams? On Zoom, maybe? It's easier to type on the computer. Anybody give me the 3 grams on Zoom? The 3 grams of computer. Giving you a few seconds. Maybe there are some people typing. Unless anybody in the room wants to try the 3 grams. Don't have anybody on Zoom. Yes, I knew it. Awesome. You are awesome. So indeed, so it looks like this. So you have so COM, OMP, MPU, that is entirely correct. C and CO, almost. What was the other? There was another answer, 2 answers on Zoom.
Yes, so the first one looks correct and the second one has the C at the start.
Exactly. So the second one is partially correct and the first one was entirely correct, right? So indeed, you have $CO, COM, OMP, MPU, and so on, TER and ER star. We don't have just C or just CO because that would be a 1 gram or a bigram, right? So when we say 3 grams, it must be exactly three letters in there containing the dollar, right? And then we have 4 grams, 5 grams, 6 grams, 7 grams, and so on. Okay. So that's it. So now in practice, of course, we might not use all of that. In practice, in fact, we like the 1 grams not so much. It's just 1 letter, so that's actually not very helpful. 5, 6, 7, that's not very space efficient. Just imagine the size, the number of terms that we would get in there, of terms in the sense of the number of k grams that we would get would be enormous. So this is kind of the sweet spot in which we find that useful, like 2 grams, 3 grams, 4 grams. This is the zone of usability, right? So now what we can do is compute these k grams, and then we can build again yet another index that's based on the k grams, right? And now, something we can do, so for example, I took 2 examples with computer and Terran, and now I can build another B plus tree using these 3 grams in that case, and all the usual structure, the usual way we build a B plus tree. And now let's have it point to the original terms, right? So every k gram points to 0, so not 0, but 1 or more terms that have this k gram. So you can see, for example, use this magic to remove the background and close this one. There you go. So you see, COM is a 3 gram of computer. ERR is a 3 gram of Terran. TER is a 3 gram of both computer and Terran, right? So that could be, for example, a singly linked list. So every k gram is associated with the list of terms that contain this k gram. This is called the k gram index. Who is with me? Okay. Now, this k gram index, you could relate it to the k-word index. Do you remember the k-word index that we use for phrase search? It's also a sliding window, but on words, right? Remember ETH Zurich, Zurich, and so on, like when we had this sliding window. It's exactly the same thing. It's just that in the case of k grams, we do it with a sliding window on letters within a word. On the k-word index, we do it on a sliding window over words within a sentence, right? But otherwise, it's exactly the same idea, right? And in fact, this duality between the notion of letter within a word versus word within a sentence is all over the place. In fact, we will see it again when we look into the vector space model in relationship with word embeddings in ChatGPT and so on, right? So k-gram index, sliding window on letters, k-word index, sliding window on words. Okay, so now imagine that somebody arrives with that query, $COM. So we are now going to, so imagine we have a 3 gram index available and the query is this. So we are going to look for which 3 gram? COM, right? It's written right there in the query. So we look for COM in our index. We know how to do it. It's just a lookup. And we see that the list of words that contain COM, there's computer. Okay, it seems that my computer has decided to do an update in the background. Oh, now it's leaving us alone. Okay, so let's let it be. All right, so COM tells us computer, and now we can look up computer in the standard inverted index, okay? So this is how I can execute a query like that. Here's another one. So I could use, of course, the permuterm index. Then I would look for TER dollar CO included, all the way to TER dollar CP excluded. Who agrees? That would be the permuterm. But if we do it with k grams, can anybody give me the k grams that we could be looking for in order to prefetch a few solutions for that query? Could have false positives, I don't mind, but what k grams would you look for in order to answer that query? Yes? $CO and TER indeed. A third one? Yes? ER dollar, exactly. Yes, exactly. ER dollar you could also look for. Yes, and somebody on Zoom agrees as well. All right. So in that case, I just looked up for $CO and TER. I could even filter for ER dollar. In the end, you will want an intersection, right? So if you do less, that's fine. You just have to filter more at the end. If you do more, if you look for more, then you will have less to filter at the end, right? So there are three of them. So if we take two, that's computer and Terran, and the intersection is computer. And if you look for ER dollar, by the way, you would also see that it would have computer. Okay, perfect. So what do we have? Let's do a recap. We can answer wildcard queries with the regular standard inverted index, with the reversed standard inverted index, with the permuterm index that has all of these rotations with the dollar in the middle, and with the k grams with the dollar at the start and at the end, right? 4 indices that we can use to answer wildcard queries. But here's something else. We can also use the k-gram index to do spelling correction. The same index, we don't even need to build a new one. So have you already noticed that when you type a word in a search engine like Google or Bing or Yahoo or DuckDuckGo and so on, if you make a mistake, it's going to have this did you mean answer. Who already saw that? All of you, right? So how do they do that? Well, nowadays, it's not only that they say, did you mean? It's that they even say, I think you meant that, and I actually went ahead and corrected your mistake, like without even asking. And you have to actually click somewhere to say, no, I don't want to correct because that wasn't a mistake, right? So you could say you always query also for the corrected terms. If not in the dictionary, that's another strategy. So you query for the corrected terms if the original one isn't found. Or you could also restrict more and say you query for the corrected terms if it's not in the dictionary and there are not enough results, because it might be that it's in there somewhere, but maybe the dictionary is not complete and there are not enough results. Or you could say, okay, no, you're just making a suggestion, right? You're not actually fixing, you're just saying, okay, you might have made a mistake and this is what I suggest that you look for instead, right? So you could make a suggestion. So these are all the possibilities. So now the big question is, how do they do that? How do we actually manage to implement a system like that? So I'll come back to the k-grams because the k-grams turned out to be a solution. But if you think of it, what does it mean to make a spelling correction or to fix a mistake in a query? There is the idea that you might have made a typo and you're typing a query that almost looks like what you're actually looking for, but there is a small typo. So there is the notion of some distance between what you type and what you're looking for, right? And you would like that distance to basically be small if it's just a typo, it's a single letter, and to be larger if it's not just a typo, but you really just typed something entirely different. So a first way to approach that is indeed in terms of defining a distance between terms, right? How do we do that? There are plenty of ways of defining distances, actually. I'm going to give you a few examples, but there are many, many different solutions. Let's start with what is called the edit distance or the Levenshtein distance, the Levenshtein edit distance. I'm going to take an example. Imagine that these are two words and I'm looking for the distance between these two words. The idea of the edit distance is how many atomic modifications does it take to go from one word to another word? So if I start with or, how many editing steps do I need to go to 2? What do I mean by editing step? I mean deleting one letter, or adding one letter anywhere, or replacing one letter with another letter, right? Your finger slipped on the keyboard and you typed somewhere else. So in that case, for example, you could say, okay, well, the distance is at most 2 because I could remove the R and then add the T, right? So that gives me an upper bound of my distance, right? And what I can define as the edit distance is the minimum such distance. I have to find the smallest possible list of edits, of these atomic edits, that go from one word to the other. And that smallest number is the distance between the two words. It might not be unique, right? There is another way. So here I have a distance of 2. I remove R and I add T, but I could also replace O with T and replace R with O, right? It's maybe more involved, but it's still 2 edits, right? But if you look, you can probably convince yourself that you will not find any way to do it with a single edit. That doesn't exist. So here the minimum is really 2. Who agrees that the minimum is 2 here? All right. But how does it generalize? How do we come up with a way to compute the edit distance? Here it's a simple example. It's just 2 words with 2 letters. But in general, what if you have a word with 30 letters and another word with 20 letters? You could go brute force. If you go brute force, you try to find out all possible ways that you could edit the words and land on the other. But this is absolutely exponential and completely impractical. Let me show you how big that is just for that example with words of 2 letters. That will let you imagine what that looks like for even larger words. So this is called a search space. I'm basically searching for a path, for a shortest path to edit that. So imagine I want to go from or to 2. I could basically think in terms of problem space, right? So imagine that I consider everything I could do. For example, I could add an O to go from R to 2, or I could remove the R, or I can remove an R with an O. And whenever I consider this brings me back to another problem, right? If I consider that I add an O, then what remains to be done is to go from or to T, right? If I know how to go from or to T, after that I can add the O, right? Or if I know how to go from O to 2, then I can just remove the R and I get the original problem. Or if I know how to go from O to T, and on top of that I replace an R with an O, then I know how to go from or to 2. Who agrees? Right? We're just cutting the problem into smaller pieces. So I start with all the possible atomic edits I could do that are meaningful to go from one to the other. And then I just reach some other problem. It's a recursion, right? It's always a recursion. I do one step and then I come back to another problem recursively. And then I again consider all possibilities, right? And again, I come back to another problem and then I again consider all possibilities that I could do, right? And then again, and I think I'm done, right? So basically I explore, look at how this is already so large for just 2 words. And I even took a shortcut because I only considered removing R, adding T and so on, right? If you consider in general, you might have even more possibilities. So this is just enormous. This is our search space. So technically, if we had a brute force approach to try to find the shortest path in there, and you can actually probably see the shortest path, right? When you see this blank, that basically means it's a trivial problem. So this would be a shortest path right here, right? For example. How do I reason about exponential search spaces? Well, let me try to tweak that picture a little bit, right? For example, so here now I'm back to the sink. So there is a source and a sink. All right, and then we can use graph theory to look for the shortest path. Now, that's an example where, for example, if I cross that path, I would basically, you can walk bottom up, right? You add a T, you remove an O, you add an O, and you remove an R, and then you basically have your the edits that go from OR to 2. But now you could use that, right? When you have that kind of searches, you can do a depth first search and traverse, go up and down and up and down and up and down, or all the way and keep only the minimum path. Or you can do a breadth first search. That's the other solution. It's good because it slows me down when it's on strike like that. I just need to give it a few seconds till it moves on. Click again. Yeah. The other one is breadth first search. Now, the breadth first search might be a good idea because then you can stop as soon as you find an ending path, right? But it takes a lot of time. But the thing is, do you see some duplicates in there? You probably noticed that there are some of the squares that appear multiple times, right? For example, we have, so all the empty squares, of course, they're all the same. This O here, it's here, it's here, it's here, it's here, it's here. You know, there's repetition in there. What if I add colors, right? Now I add the colors. And I noticed that I have an equivalence relation, right? Some of my problems in there are equivalent problems. So now I can take the search space. I have an equivalence relation. And between problems in the same class for my equivalence relation, it's the same, right? If I know how to solve the problem, it doesn't matter where I am in the search space. What can you do when you have a set and you have an equivalence relation on a set? You can compute the start with a Q. You saw it in discrete math, probably. Quotient sets. Who heard of quotient sets? You didn't hear of quotient sets. I'm going to explain then quotient sets. Okay. So the idea is that we group together what has the same color, right? So the quotient set is basically this. If I have grouped everything into classes like that, then I merge everything that is in the same class as a single element. This is what we do. Who heard of Z over 2Z, right? The Booleans. If you have an equivalence class that you have all of the odd integers and all the even integers, then you can group all of the odd integers in a class that you call 1 and all the even integers in a class that you call 0, right? So here it's the same. I have my class, and now I have just one single representant for the entire class, and I have this simplified view. There is just one assumption in there that I'm making. I'm assuming that the edges that go between colors, they don't depend on the specific choice of the very square you put with a specific color. For example, there are arrows that go from red to yellow, from purple to yellow, and from orange to yellow. I'm going to show here. So we have an arrow that goes from here to here, from here to here, and from here to here, and another one that goes from here to here. Well, if you look on the original one, that's also always the case. If you look at the entire one. So you have some, you need some compatibility in there between the sort of operation you're making on your set and the quotient set, right? So if you have that, then you can simplify everything and take the quotient set. But now, do you see why I like that? Because that's actually quadratic now. I rotate a little bit. This is, in fact, a rectangle. And that I love. Who heard of dynamic programming? This is dynamic programming. I just explained it to you in this way with the quotient set, but this is why we have dynamic programming. It's basically taking a quotient set on a gigantic space that is exponential. You group the problem into smaller classes in a way that it becomes quadratic, and then you fill some rectangular shape recursively. And that's it. Whoever heard of dynamic programming in this way? Okay. Some of you. Okay, awesome. So it means that we can compute the edit distance between two words in polynomial time. All we need to do is have this structure that basically has the two words in the rows and in the columns. I start on the top left, and then I just fill that recursively. So sharp is for a marker for when it's empty. So the distance between a word and the empty word is just the number of letters, right? Because the edits I can do is just delete one by one all of my letters. So this, the first column and the first row, these are easy to fill. right? Just increasing integers in there. Now, the question is, how do I recursively fill that table? So I just need to go from left to right and from top to bottom, actually in any way that I want. And the idea is that for every single cell that I want to fill recursively, I consider the 3 possible edits. For example, if I want to go from cat to 8, then I could consider going, if I have from C to A, I can add an A, I can replace what is written here, I can substitute A for C, or I can add a C, right? So it means that, let me think if I did it with the other way in mind. Now my mind is going blank. See. So this is, imagine that, yes, exactly, this is how you start. So you want to go from A to C. So you can, if you know how to solve it from the empty word to the empty word, it's actually trivial. Then you replace the A with a C, and then you are here. If you know how to solve it, that you go from, so it's the other way, from C to the empty set. You go from C to the empty set, and then you add an A, then you went to C, from C to A. If you know how to go from the empty set to A, then you go from the empty set to A, and then you have this additional step of adding C. I think this is the reason that my mind goes blank and I'm confused. I confuse the add, remove, and so on and so on. So this is something that I will need to redo the slides. I can try to repeat if you want. Who wants me to repeat? Who understands? Okay, you're raising your hand. So basically, the idea is simply that if you know how to solve this problem, go from the empty sets to the empty word to the empty word, then you can solve that problem and then substitute the last letter with another letter. If you know how to solve that problem, going in that case from the empty set to A, then you go from the empty set to A and you remove C. And if you know how to go from C to the empty set, then you can go from C to A by doing first that and then adding A. So basically, every problem you can solve by recursively solving one of these 3 problems and then one edit, right? So then, if you consider that this adds 1, if you know how to solve this problem in 1 step, this is plus 1 step, so that's a 2. If you know how to solve this problem in 0 steps, you add a 1. And if you know how to solve that problem in 1 step plus 1, that's a 2. And the minimum step here would correspond to 1, right? So this would be this one, okay? So this is the idea that every time you consider the 3 possible edits, and then you take the minimum. So if I go from here, for example, I consider 1 plus 1, 1 plus 1, 2 plus 1, that's 2, 2, and 3, and the minimum is 2, right? If I want to go here, 2 plus 1 gives me 3, 2 plus 1 gives me 3, 3 plus 1 gives me 4, the minimum is 3, right? Then I continue, 2 plus 1 is 3, 2, 2, so the minimum is 2. Here I can have, you see, every time I do that, and so on, and I fill that, right? Every time I do plus 1, plus 1, plus 1, and I take the mean, and I go left to right, top to bottom. All right? Who is with me? Who would be able to fill that table on any example? Okay, all right. There is just one thing to consider, is that when you go diagonal, you need to consider the case that it's not equal or that it's equal. Because in the case that it's not equal, this is an actual substitution that is a step of 1. In the case that it is equal, here you're substituting A with A, that is not an edit, that is 0, right? So in that case, when you went diagonally from here to here, replacing A with A doesn't do anything. So this is why here, in these cases, you don't add 1. Right, so you add 1 in all cases except where this is the same letter. Okay, so this is the edit distance, and then you can even keep track of the pointer that gave you the mean, and that allows you to navigate at the end. So you have the edit distance between the 2 words cat and 8. That would be here. The edit distance is 2. And you can follow the pointers that basically you put whenever you had the minimum. You can follow backwards like this, and that gives you all of the intermediate steps. Okay? We deserve the break, right? Especially after I confused you with the way that I tried to explain the recursion. All right, so I will see you in 15 minutes, and then we'll continue with more ways to do spelling correction. All right, thank you very much.